Physics 2212, Lab 5, Magnetic Braking. So for the introduction, the purpose of this lab is to collect data of a magnet falling through an aluminum tube to learn the effect of Faraday's law. Important physics principles are Faraday's law, of course, Lenz's law, the Biot-Savart law, a time derivation of magnetic flux, and of course Newton's laws. Off to the right shows the equation for Faraday's law, and the one below is the Biot-Savart law. And then results are experimental time was 1.25 seconds, and then the predicted with GlowScript was 1.19. So continuing that introduction, the model of it is we are representing the magnetic behavior with a simple dipole model, assuming that air resistance is negligible because the force's magnitude is insignificant. So the only force on the magnet is gravity and magnetic force. So the system versus surroundings. The system is just the magnet and the aluminum tube. The surroundings are the Earth. The initial conditions are the magnet sits at rest at the top of the tube and then is dropped. The procedure is we used a magnetometer on my phone to determine polarity of the magnet, and then we put a stopwatch in the background of the video and drop the magnet 5 times, and then we analyze the video to get data. So here's the experimental data. On the first trial, we got 1.25 seconds, and the next one was 1.23, then 1.32, 1.22, and then 1.23. Two dimensions, the length was 0.3 meters, the wall thickness was 0.6 centimeters, the outer diameter was 0.06 meters, and then the inner diameter was 0.048 meters. The magnet measurements was mu is 2.21, the magnet mass is 25,000 kilograms, and then the average time was 1.25 seconds. So checkpoint questions: why can't we use a Ferris tube? Can't use a Ferris tube like stainless steel because it contains iron, which has magnetic properties, which is not the behavior we are seeking for in this lab. And then the next question: what happens to the magnet? How does this compare to a magnet falling in free space? The magnet falls significantly slower than in free fall because the induced current from the tube provides upward force on the magnet. So here's the first part of the GlowScript code. We have physical constants and then graph initialization. And then continuing that, we have step 1 where we plug in the dimensions of the tube. And then we have the numerical parameters of the simulation. And then we create the tube of aluminum foil for the visual. So more GlowScript code here. We got a lot of stuff. Initial conditions, creating the bar magnet, defining the dipole, and then calculating the actual magnetic flux, and then the while loop, which does the calculations of the actual motion of the magnet. So this is the last slide of GlowScript code. We calculate the change in flux over time, and then we color the ring and the visual, and then we calculate the magnetic force, and then we calculate the net force, and then apply Newton's second law to update the position of the magnet. So here are the graphs that we took from the GlowScript model. On the right, you can see that it falls with a pretty constant velocity. In the middle point, that's where it reaches equilibrium. So here's the visualization the GlowScript outputted. The blue is the south pole, which is negative, and then the red is the north pole, which is positive. So for the questions, for question 1, red is counterclockwise, blue is clockwise. For the second question, nothing other than the direction of the current flips, the magnet will still fall at the same speed. For the third question, they are very close, and when using the correct mu value, which is adding more rings. And then for the last question, it is unbalanced, balanced, then balanced. All right, so for the conclusion, no significant discrepancies between the model and reality. The dipole model is very accurate. Potential sources of error is bad time data from the experimental data because of low frame rate and any errors for calculating mu in lab 3. What is the resistivity of the conductor? Were reduced as close to 0. How would the dynamics change? Due to Ohm's law, induced current is much greater. So then magnetic force will increase, slowing the magnet further. What if holes or slots were cut into the tube? How would this affect the ring currents in the model? There would be no induced current in the rings of the tube where there are holes or slots, so the magnet would move a lot faster when going through those parts.